I'm Doug Fern, and this is my take on music recording. If you take the covers off a piece of studio equipment, what do you see? It's probably a big printed circuit board with many components of various sizes and colors. Some parts have numbers and words printed on them. Others may have nothing to help you know what that part you are looking at actually is. If you wanted to understand how all those random parts work to make an equalizer, a compressor, a channel strip in a console, or a converter, where do you start? You may be able to see that the parts are soldered onto areas of copper that form the traces that interconnect the parts. But those can be difficult to follow. Most PCBs have a coating over everything, often green, but it could be any color. And to make it even more mysterious, most circuit boards have traces on both the top and bottom. And complex digital equipment may have many layers of traces buried internally within the board itself, invisible to the eye. Trying to figure out how something works by looking at a PCB is guaranteed to be frustrating, time-consuming, and prone to errors. And the parts are also a mystery. How do you go about understanding how the gear works? This was easier in the era of point-to-point wiring, like in most gear produced before the 1960s, or in current production products that utilize that classic technique. All the DW Firm products, for example, use point-to-point wiring for the entire audio path. We do use circuit boards for some things, like in a power supply. Point-to-point construction has many advantages, namely better performance if done well, and easy replacement of parts should that ever become necessary. Point-to-point construction also makes it very easy to understand how a circuit works. The key to understanding a circuit, whether it is built on a printed circuit board or wired point-to-point, is a map that shows you how every part is interconnected. And for that, we use schematic diagrams. It used to be that all equipment came with a manual that included a set of schematic diagrams to aid in troubleshooting and repair, but very few manufacturers do that anymore. Most of our current recording gear is not designed to be repaired. Understanding what a schematic diagram is telling you can be a useful skill, even if you only use it to draw a diagram showing how all your studio equipment is interconnected. Learning what the symbols mean is not difficult. Obviously, a schematic diagram is a visual tool, and this is an audio podcast. A good online overview of common schematic symbols can be found at the link in the description below. At some point, I may make a video showing what the symbols look like, but for now, I will just describe them. There really aren't very many, so let's get started. One of the most common components found in any equipment is the resistor. Its symbol is simply a jagged line. It's showing you that the electron flow through a resistor encounters a more challenging path than a simple piece of wire. It impedes the flow of electrons, as I talked about in part 1 of this series. Resistors come in many different sizes and shapes, but their fundamental purpose is always the same, and the schematic symbol is always the same, except some schematics, mostly for gear manufactured in countries other than the U.S., may use a different symbol, usually just a small rectangular box, but mostly you will see the jagged line. To show wires, or their printed circuit equivalent, a single line is drawn showing what connects to what. Simple and intuitive. An unadorned line is a wire. The schematic diagrams for most equipment uses a ground symbol. This indicates a common point in the circuit. Often, the negative output of a power supply is connected to ground. Bypass capacitors usually have one side going to ground. Pin 1 of XLR connectors on the equipment is connected to ground. The ground pin of the incoming AC mains voltage goes to ground. The symbol used to show a ground connection has many variations. The traditional symbol is simply a series of parallel lines decreasing in width at the bottom. The grounded element of the circuit connects to the top of this stack. A variation of this is just a triangle. Other variations include a horizontal line with 3 legs on the left, middle, and right of the line, drawn at a slight angle. Sometimes ground is shown just as a horizontal line. All those symbols are shown with a connection at the top. Some equipment, notably digital audio equipment, often has more than one ground, usually one for the analog portion of the circuit, with a different ground for the digital part of the circuit. Different symbols might be used, or the ground symbol may have a letter inside the triangle indicating whether it is an analog or digital ground. The whole concept of ground is misunderstood by many people. It can be a lot more complex than you think. An upcoming episode in this series will discuss the ground concept in detail. Another common component is a capacitor. Its symbol reflects what is going on inside a capacitor. It shows 2 parallel lines with a wire extending out to either side. There is a gap in the middle. That's how a capacitor is built internally. For our purposes of understanding the symbol, you could think of it as a device that blocks direct current but permits alternating current to pass. Some types of capacitors, like electrolytic and tantalum capacitors, are polarized. They have a negative and positive side, and connecting in the wrong way will usually damage them. They can even explode or catch fire. The schematic diagram will show a plus sign for the end of the capacitor that must go to the positive voltage in the circuit. A transformer is shown as 2 coils of wire separated by several solid lines. That shows how a transformer works, with 2 coils of wire wound around an iron core. Many transformers have multiple windings or taps along the winding, and those can be shown as well. An inductor is just a coil of wire, usually wound around an iron core in audio devices. Its symbol looks like half a transformer. Resistors, capacitors, and inductors can have variants that are adjustable. The most common is the pot or fader. Its schematic symbol is the usual resistor with an arrow intersecting it at a right angle, with its own wire going to a point in the circuit. Most often, variable resistors are 3-connection devices. Variable capacitors and inductors are still usually 2 lead components. When they are variable, there will be an arrow going through their schematic symbols at an angle. You won't find many of those in studio equipment. They are mostly found in radio frequency circuits. In audio equipment requiring variable capacitance or inductance, that is usually done with a switch and multiple capacitors, or an inductor with additional wires coming out from taps along the winding. Most equipment has switches. They are used to turn things off and on and for selecting a function from a variety of options. The simplest switch is just an on-off switch, like you might find to turn equipment power on and off. This is called a single-pole, single-throw switch, and its schematic symbol is an arrow aiming at a dot. The arrow represents the movable part of the switch, and the dot is the contact. The movable part, the arm, can either connect to the dot or not. If it connects, the circuit is completed and is considered on. We call the switch open when the current cannot flow and closed when it can flow. This is contrary to our everyday usage of open and closed. You can't go through a closed door. I like to think of the schematic symbol for a switch like a drawbridge. You can only pass over it when it is closed. This simple switch, often called SPST, is one kind, but many switches are more complex, some a lot more complex. We can expand on the SPS term as needed. For example, a DP-DT switch has 2 poles and 2 possible positions. It can switch 2 things at once, say a balanced audio line, or it can select one of 2 possible sources or destinations. A rotary switch is similar, but its symbol is circular. It allows you to select many different destinations, and it can have multiple poles to switch multiple things at once. Rotary switches can be very complex, and tracing out what it is doing can be challenging when trying to interpret a schematic diagram. A lot of current audio equipment does not use physical switches, but rather digital circuits that perform the same function. This can be confusing in a schematic diagram because digital logic ICs are used for the switching, or an embedded computer controls the electronic switches. There are an endless number of digital ICs, each with different characteristics and ratings. That's beyond our discussion here. All digital circuits are, at their core, on-off switches. To emulate a conventional switch, a transistor can be configured to be an electronic switch. The function is the same, but there can be an audible difference in the sound between the physical switch and its digital equivalent. A device related to a switch is the relay. It can be simple or complex, but generally there are no rotary relays in common use. A relay is a remote switch. I described it in part 2 of this series. A relay is shown like a switch, but also includes a symbol for an electromagnet, which looks the same as an inductor. Like any switch, a relay can have multiple poles and multiple positions. A double-pole, double-throw relay is common. A separate switch controls the relay. One mechanical switch can control multiple relays when complex switching is required. Every piece of audio equipment has to have some way for the audio to get into it and out of it, and for that we use connectors. Devices with just 1 or 2 inputs and outputs usually use XLR connectors, the same as what we use for microphones. More complex equipment, like a converter or a console, needs a lot more inputs and outputs, and they are often on larger connectors that typically have 25 contacts, which can accommodate 8 channels of balanced audio. Some vintage equipment uses screw terminals for external connections. No matter what type of connector, the classic, generic schematic symbol was simply a V shape for an input and an arrow shape for an output. Those represent the male and female connectors. The symbols I have covered describe most of the passive components you will likely find in an audio device. Active devices are the ones that actually amplify the audio passing through them. The 2 main categories of active devices are vacuum tubes and transistors. There are many variations on these symbols to represent different subtypes of these devices. Let's begin with vacuum tubes, since they came first. The schematic symbol for a tube is a circle with several lines inside. You can think of that circle as the glass envelope that goes around the internal parts. There is no air or other gas inside, of course. It is a vacuum tube. Tubes come in several varieties. I will describe the ones you will find in audio equipment. On most tube diagrams, you will see at the bottom of the circle, inside, a triangle. It's just two lines that go up at an angle and meet in the middle. They are drawn symmetrically. Those represent the filament, which is heated by electricity and glows dull red or orange. That is the light you see inside the tube. It's the same concept as an incandescent light bulb, only a tube does not need to produce light to work, only heat, so it is a dull red and not the bright white light of a light bulb. The purpose of the filament is to create a source of electrons. In the early days, the filament produced the electrons directly, but since the 1930s, most tubes have another element that surrounds the filament and is heated by it. That is called the cathode, and it is shown like a roof over the filament with a little downward hook at the far end. On the opposite side of the tube, at the top, is another internal element called the plate, sometimes called the anode. Its purpose is to receive the flow of electrons emitted by the cathode, and, in a circuit, provide a path for those electrons to leave the tube. If there are just two elements in the tube, it is called a diode. Notice it has the same name as the solid-state device, also called a diode, described later. In the audio world, a diode is used to convert AC into a raw form of DC. The AC could be the 50-60 Hz mains voltage, or it could be audio. You won't find many vacuum tube diodes in audio gear these days, even in equipment that is otherwise all tube. The solid-state diode performs the same function and is much smaller and cheaper. In between the cathode and plate is a dashed line. This is the grid, and the schematic symbol in the tube shows how it is a grid of wire, like a fence. This is the control element in the tube. It's the handle of the valve in that analogy. Its purpose is to regulate the flow of electrons flowing from the cathode to the plate. Putting an audio signal into the grid allows it to control a much larger current in the cathode to plate circuit, creating an amplifier. The three-element tube with a cathode, grid, and plate is called a triode. Note that the filament is not part of the amplifying circuit, so it's not counted as an additional element. If a tube has two grids, it's a tetrode, and three grids creates a pentode. Special-purpose tubes can have more grids, but they are not used in audio gear. Triodes are most common. Tetrodes and pentodes are used in power amplifiers to drive speakers. Tubes with additional grids are shown schematically the same as the main grid, only between it and the plate, in the same order as they are arrayed in between the cathode and plate. For more on how vacuum tubes function, listen to the episodes Vacuum Tube Fundamentals from May 2021 and Vacuum Tubes, Why They Sound Better for Audio from July 2020. Some form of solid-state electronic devices have been around since the early 20th century. Initially, there was just solid-state diodes, very different from what we have now. The schematic symbol for a diode is simply a vertical line that is intercepted at its center by an arrow. A solid-state diode, like its vacuum tube counterpart, only allows alternating current to flow in one direction. The parts of the diode are called the anode and cathode, corresponding to the plate and cathode in a tube diode. The active amplifying device in audio is the transistor. Its schematic was derived from the vacuum tube symbol, modified to show how it functions using a different principle. It is shown as a circle like a tube, but the internal parts are different. It partly looks like the symbol for a solid-state diode, with a bar and an arrow intersecting it. But in the transistor, the vertical bar is intersected by an arrow coming up to it at an angle. And the third element of the transistor is simply a line that intersects the vertical line at a right angle, conventionally coming from the left side of the circle. Those three elements are called the emitter, base, and collector, and very roughly correspond to the cathode, grid, and plate of a triode vacuum tube. Transistors do not have additional base elements, unlike tubes that can have more than one grid. What I just described is a bipolar transistor, the first kind invented in 1947. Since then, a variant called the field effect transistor, or FET, was developed. The FET has characteristics that are closer to a triode vacuum tube compared to a bipolar transistor. And the FET is the type of transistor used in most audio gear dealing with low-level signals. The symbol is similar to the bipolar transistor schematic symbol, but drawn in a more rectilinear fashion. You won't find many transistors in modern audio equipment. Any transistors that are used are usually called discrete transistors, to distinguish them from the nearly universal amplifying device in audio gear, the integrated circuit. Discrete transistors may have some sonic advantages, but the integrated circuit is king in modern equipment. The integrated circuit was developed in the late 1950s. It combines several transistors on a single piece of silicon, the same material the transistors are made of. The advantage is that an integrated circuit, or IC, is much smaller than a bunch of individual transistors. That allowed equipment to be much smaller. The IC is a brilliant invention, and it makes our modern society possible. The vast majority of ICs are used in digital devices, but there are also some that were developed for audio. The schematic symbol for an IC is usually just a rectangular box, with various wires coming into it and out of it on all sides. But one category of IC is called an op-amp, short for operational amplifier. This circuit was developed in the 1930s, primarily for analog computers, the type of computer made before the digital age. The early op-amps were made from a collection of vacuum tubes, and they had a very specific purpose, which was processing various analog inputs and outputting an analog voltage. That was used for such things as aiming artillery during World War II and for a long time after the war. A solid-state version of the op-amp became widely available in the 1960s and made the modern recording console possible. An op-amp IC can have dozens of individual transistors inside. By comparison, a digital IC could have thousands or even millions of transistors inside. The op-amp has its own symbol, which is a triangle with a pointy end facing to the right. In tubes, often the filaments of the tubes are not explicitly shown on a schematic diagram. The filament symbol in a tube and its associated wires is implied, or perhaps they are shown separately on another part of the schematic diagram. The same applies to the power wires going to an op-amp or other IC. Leaving those wires off the drawing makes it easier to follow the signal path. Anyone familiar with the way tubes and ICs work would know that the power inputs are required, so showing that wiring is unnecessary. Some other symbols you may encounter are a sine wave shape representing a fuse, or a circle with a diagonal line inside to show a meter. If the equipment has a motor inside, perhaps for a cooling fan or in a tape machine, the symbol is usually a circle with an M inside. There are many other schematic symbols for specialized electronic parts, but the ones I have described cover most of what you will find on a schematic diagram of audio equipment. It is often helpful to draw a simplified schematic diagram that does not show all the individual components, but rather an overview of the signal flow. For that type of diagram, the amplifier symbol, which is the same as the op-amp symbol, is used to show gain stages. Subassemblies, say an equalizer circuit, might be shown as a simple rectangular box. That shows the purpose of a component or group of components, but at a reduced level of complexity. Such drawings are often called line diagrams. There are various ways to indicate the actual value of the parts in a schematic diagram. That could be the value of a resistor in ohms, kiloohms, or megohms, or a capacitor in microfarads, nanofarads, or picofarads. Parts of a particular type, like a tube, a transistor, or an IC, might show the model number on the schematic. Some parts, like resistors, might have a wattage rating as part of the value, and capacitors might have a voltage rating. Note that some schematics may not have any values shown. Most manufacturers include a unique name of each part, using standardized nomenclature. For example, resistors might have text next to them showing R1 and up across the diagram. Sometimes resistor numbering might begin with R100 for one subassembly and R200 for the next subassembly. There should be some logic to the assignment of these component numbers. I like to start with R1 for the first resistor the audio encounters and continuing in increments up to the last resistor in the circuit, typically near the output. But that can be difficult to maintain precisely during the design stage, so often schematics may seem to have random numbers. In the old days, an important part of the manual for the equipment was not only the schematic, but the description of the part in a listing. For example, R1 might be described as 100K ohms, 1/2 watt, 1% tolerance, metal film. That makes it easy to find an exact replacement part, should that ever be necessary. Without that complete description, someone making a repair might just pick a generic 100K resistor, which might or might not work properly in the circuit. Some other conventions for labeling of parts includes letters like J for jack, L for inductor, P for plug, T for transistor, V for vacuum tube, Q for transistor, and U for an integrated circuit. Most of those make sense, but U for an IC? That came about decades ago when ICs were first introduced. Legend has it that U stood for unrepairable, which makes sense. The U has remained ever since. There are multiple explanations for why Q is used for transistor, none of which seems definitive. Other countries have their own component nomenclature, so schematics for that equipment may have things like TR for transistor. The V used to designate a vacuum tube works for both the U.S. term and the British term valve to describe the same device. Not all schematics use the symbols I described. Some components may be shown very differently, like a small rectangular box for a resistor, or drawing tubes or transistors without the enclosing circle. Switches, too, may be drawn in many different ways. Sometimes a rotary switch needs to progressively short out various components connected to it. That may be shown with a symbol that looks a lot like the actual switch mechanism. No matter how those parts are drawn, they have to be interconnected by wires, or their PCB equivalent, traces of copper. Those are shown on a schematic diagram as simple lines connecting the various parts together. Seems simple, but how you draw the schematic has a big effect on how easy, or how difficult, it is to trace out the path in a circuit, or understand what is going on in the equipment. By convention, only horizontal or vertical lines are drawn on a schematic diagram, no diagonal lines. no lines that weave around, changing angles as they continue to their destination. This makes it easier to read the schematic. There are two different approaches to how wires cross or connect. One just crisscrosses the various wires as they go between parts, with a dot at the junction to show a connection. That is a simple and quick way to draw the diagram. Some drawings don't even use the dot. The other way is to use a jump symbol to show where wires cross but they do not connect. The symbol is just a semicircle that goes over the wire. I find that easier to interpret at a glance than the wires that just cross. In that approach to drawing a schematic, dots may or may not be used to show a connection. If a wire ends at another wire, they just join at a right angle. When I draw a schematic, I use both the jump symbol and the dot to show a connection. That takes a couple of extra steps to draw, but it is unambiguous. I always look to the future since I design my products to last at least 50 years and be easily repaired if necessary. Old diagrams on paper become notoriously difficult to interpret, especially if they have been folded. And although most people will only see schematic diagrams on a screen, I want to make sure that my schematics can always be easily read and interpreted. Note that my descriptions of schematic symbols describe how they look in a horizontal presentation. The individual parts, especially resistors and capacitors, can be shown oriented vertically as well, which often makes understanding what is going on in the circuit easier. And that brings me to another point about schematic diagrams. If someone wants to make the operation of a piece of equipment simple and intuitive for someone looking at the diagram, it is best to draw it in a way that describes how the various audio signals and DC power circuits work. In the old days, schematic diagrams were drawn by hand by a draftsman. They made beautiful schematics that were simple to read and showed you instantly how the device worked. The diagram generally followed the signal flow from the input on the left to the output on the right. That made it easier to follow the path that the audio took from input to output. Today, most circuitry is built on printed circuit boards, and the software used to design those boards is sophisticated and complex. But it always starts with a schematic diagram that is input into the software. From there, the parts and their interconnecting wires can be interpreted by the program to help speed the board design process. It works really well, and modern complex electronics would be difficult to design any other way. But those automated functions in the design software do not care about readability of the schematic diagram, and the designers have no incentive to make the schematic easy to interpret. So the resulting schematic diagrams are simply what the operator inputs and the board design software outputs. Those schematics can be very confusing to read and interpret. They make it more difficult to troubleshoot a problem on the board. But then, the board was never intended to be repairable, so there is no incentive to create a clean schematic. Simple equipment can be drawn schematically with everything in one drawing. But with more complex equipment, multiple schematics must be used. For example, the DW Fern VT7 compressor needs 5 separate drawings, and that means the wires connecting the various parts of the circuit must be labeled, showing where they come from or where they go. That can make tracing out a circuit and following the audio and power paths more difficult. But the alternative is to make one giant diagram, and that is not helpful because it will require a huge piece of paper or paging around the schematic on a screen. Usually the most challenging part of reading a schematic is following a mass of wires for power distribution or multiple audio paths. That can result in many parallel wires, shown as lines. There could be 20 or more of those parallel lines in some equipment. Tracing how the various signals get from one place to another requires following those closely spaced lines on the diagram. That process is tedious, but the worst problem is that it is very easy to jump the track from one wire to another, making understanding the circuit frustrating and error-prone. Figuring out the actual circuit can be difficult. You need a lot of patience. It gets particularly frustrating when the diagram is spread over multiple pages. A good drawing style makes it much easier. Learning how to read a schematic diagram and creating your own is a valuable skill if you want to have deeper insight into how the equipment we use every day actually works. Thanks for listening, commenting, and subscribing. I am always interested in hearing about which topics are most useful, and I want to hear about other topics you think I should cover in the future. I can be reached at dwfern@dwfern.com. This is my take on music recording. I'm Doug Fern. See you next time.